This is the last type of the problems that we have to prove in mathematical induction. That is the derivatives. Okay. Now it says prove by mathematical induction that these uh, 2nth derivative of this is this. Okay. So this is basically 2nth derivative. So you have your y is equal to uh, cos of 1 minus 2x, and we have it here. I'm not going to write this again. Okay. So now let us differentiate this, because our first step is to prove this. We have to prove this for n equal to 1. So basically, I have to prove that d2y, I'm just substituting this n as 1 here, d2y by dx squared, that is equal to minus 1 squared, and then you have 2 raised to power 2, okay, and then you have cos 1 minus 2x, and this is 4 cos 1 minus 2x. I have to prove
Where it's
this.
never be 2 square. It's only, acha, आपने, okay, sorry.
Okay, now we have to prove this. Okay, so now let us show our muscles on differentiation. So I'll first of all find dy by dx. So that is going to be minus sine 1 minus 2x. Remember, the derivative of cos is minus sine, and then the derivative of its angle is going to be minus 2. Okay, so this is going to be 2.
Sir, I was saying कि n जो है ये माइनस है ना, तो -1 के ऊपर जब 1 आएगा तो ये -4 होगा.
But there is
-1 square हो रहा है तो positive 1 square नहीं हो रहा ना, वो n है सिर्फ. It's not 2n.
एक second. I think she has a yeah, you are right, beta. I by mistake I have put here this this 2 here. You are absolutely right. Thank you, beta. This is minus 4 cos this. Thank you once again for saving us from the disasters, because otherwise we could have been in trouble here. Okay, now I'm going to differentiate this again. This is d2y by dx squared. So I have 2 cos 1 minus 2x, and now the derivative of this angle is minus 2. So we have minus 4 cos 1 minus 2x. Okay, and this is what we had to show. So we have shown that this is true for n equal to 1. Okay, second step. Now we shall assume that we shall say let it be true for n equal to k. So what we have here now is going to be, this is d raised to power 2 ky over dx to k, and that is equal to minus 1 raised to power k and 2 raised to power 2k, and this is cos 1 minus 2x. Now we have to, in the third step, we have to prove that this is true for, I'm going to cover this area here because I don't need this. So I'm going to cover all of this. Okay. Now we are going to enter into the third step here. We're going to prove that, let's prove this, prove it true for n equal to k plus 1. Now in our minds, we have here that we have to actually show that this d2, and I change this with nk plus 1. This is going to be 2k plus 2y over dx 2k plus 2, that is equal to minus 1 raised to power k plus 1, and then into 2 raised to power 2k plus 2, or 2 into k plus 1, and cos. So we have to bring this in our lives. Okay, this is our mission. Okay, so We're going to prove it true for nk plus 1. Okay, so we need this d2k plus 2. So um, so we have already got with us d2k y over, we'll be using this fact, okay, over dx2k, that is equal to minus 1 raised to power k, 2 raised to power 2k, and there is cos 1 minus 2x. Okay, guys, be very careful now. Acha, one thing I just want you to in this area, I'll ask you one thing. You see, when you have dy by dx, okay, and if you do it d by dx up to this, so this becomes d2y by dx square. Okay, so if it was already d2y by dx squared, then this could be d cube y over dx cube. And instead of this 2, if you had k over here, okay, so can I say this would now be d to the power k plus 1 and this dx to the power k plus 1? Yes, Pacho?
Yes,
है
sir.
ना? अच्छा, so we'll be using this fact here and we'll be differentiating this twice so that we have on the left hand side this d2k plus 2. Okay, so let's do that. So I'll be differentiating, I'm just saving some place here, I'm differentiating this side with respect to both the sides with respect to x. So this would become d raised to power 2k plus 1y over dx 2k plus 1. Okay, it's a constant, I'll let it be the way it is. This is a constant, I'll not touch it, but I'll be differentiating this. And this would be minus 1. I'm intentionally writing this minus 1, okay? And this is sine 1 minus 2x. And again, I'll intentionally write this as minus 2 because I want to add into the powers of the minus 1s and this 2. Now, when you multiply these two together, you have minus 1 raised to power k plus 1. When you multiply these two together, there was a minus 2 over here, I think, when we started. This is, oh, this is 2 raised to power
It's
2.
at the end.
Huh? So no problem. I can write it minus 2 over here. Why can I write minus 2 over here? Hmm?
Because it's being squared, so it doesn't matter.
Yeah, there is no difference in because there is an even power onto it. Okay, so this is going to be minus 2 raised to power 2k plus 1, and we have this sine 1 minus 2x. Now let's differentiate this again. Let me use a different color here. So I'm just to save my space here, I'm going to differentiate this again. So this is going to be d by dx of all of this. Okay. So this left hand side is going to be what we are looking for. Okay. And this is dx 2k plus 2. Okay. Again, these are constants. We'll just be writing them as it is. This is 2k plus 1. And now its derivative is going to be cos 1 minus 2x and times this minus 2. The derivative of this angle 1 minus 2x. So this becomes, I'm going to write this in red now. So this is going to be minus 1 raised to power k plus 1. And then there is minus 2 raised to power 2k plus 2, and you have cos 1 minus 2x. So it is absolutely the same as you were looking over here, okay? Because, since there is an even power, so this makes no difference if it is a plus or a minus power here, okay? So time to write the conclusion. We have proved this correct. So we would be writing that conclusion here. Okay. Um, as true for n equal to 1 and if true for n equal to k, then n equal to k plus 1. So it is true for all n. So this ends here.